Okay. Karol and Michael, thank you so much for coming. Karol is the co-founder and CEO of Physical Intelligence, or PI. Michael is a member of the technical staff. Physical Intelligence is building general-purpose physical AI and robotics models. The company has raised over $1 billion, and in my opinion, one of the most ambitious startups in the world right now. Perhaps just to kick it off, but for folks that are new to the company, what is PI building and what is the company mission?
Hi, everyone. Thanks for having us. We are building robotic foundation models. What I mean by this is these are the models that, in principle, should be able to control any robot to do any task in any environment. The way we think about this is that we believe that the true bottleneck to robotics is intelligence, and it has always been intelligence. So rather than building another robotics company, we really want to tackle this problem head on and focus on the intelligence problem. So this is kind of the first-class citizen for the entire company, and then everything else stems from that. It doesn't mean that we just are building software. We're also building a lot of other things. We have big operations. We build a lot of hardware in-house. We are doing a lot of different things to make sure that we can solve that problem. But it all stems from the fact that intelligence is the bottleneck, and we really want to solve it. We believe that once we do, that would lead to the world where there's robots everywhere, that robots are actually happening, and any robot will be able to be powered by our models.
As a research startup for both of you, you're making big company direction bets where there's very little precedent. If you achieve your vision, you will be an N of one company. What are perhaps some of the big disagreements in the industry on directions today?
And I think there's a fairly obvious one, which is the form factor. A lot of people are talking about the form factor, like what is this actually going to look like? Is it going to be humanoids? Is it going to be like arms strapped to a table? Is it going to be something in between? And I think there is also like a kind of meta point on top of that, which is like, does it even matter? And that's like a really big sort of tension across the different players. There's a lot of big bets on like, we're going to build like the greatest single humanoid hardware, and that's going to be like the product that like takes over the world. There's also people who are more like, we're going to build like and I guess this is kind of like PI's take, which is intelligence, physical intelligence in particular, is going to be cross-embodied. It's going to be able to control humanoids. It's going to be able to control other things. And maybe in the long run, what actually wins out is like the best form factor for a particular application. In a warehouse, you probably don't need the legs, so maybe you like drop the legs for that, but you keep some of the sort of the dexterous hands, so you can still do all the diverse different tasks that are there and like have yet to be automated. I think the other big one is there's a lot of questions around SIM, and this also stems around like just generally a problem around data and a problem around evaluation. And I think there's sort of disagreements and tension about like how important is SIM, what kind of SIM should we be building. On one hand, there's like classical simulators. This is like take all of our knowledge about physics and bake it into a computer, and use that to test policies or collect data and try to go into real. This has worked extremely well for locomotion. So a lot of like the locomotion demos, the demos of like dancing robots, it like stems from sort of this branch of the technology. But the sort of question remains like how applicable will it be to manipulation? And I think one of the corporate challenges there, and which is why like PI takes a very sort of real-world first approach to data collection, is in simulation it's more about modeling like your own embodiment. So if you can simulate like you the robot, then you can actually get a lot out of it. And then for the manipulation case, it's actually more about modeling like what happens when you touch an object, or like how do these objects behave in the real world? How heavy is like a bottle? And that's very hard to simulate in sort of like the broad cases. So I think that's kind of the tension that exists there. I think there are still people who think that can be done, and there's a lot of different people trying different approaches, and I think we'll see how it pans out in the next couple of years.
On the internal disagreements, we talked a little bit about it on the drive here. I was like, Michael, what are the biggest disagreements you know of? And I really liked your answer, which was it's less of a disagreement, but it feels more like we don't have the data. It just feels more like uncertainty. So it's not that one person is very much convinced that we need to go this way, the other person is really convinced we need to go that way. It's more like there is no data to be had. So we really need to discover the truth. There is truth. You just need to go and discover it. I think maybe the other one, which is also reflected in the broader industry, is how close are we? Right? Like I think one big thing that we've seen with language models is that many people in the industry had thought that there's many, many more things to be developed before we will have something like ChatGPT. But it turned out that all of the technology was basically there, and you just needed to scale it up. And we have quite a bit of debate internally on how much should we scale the existing thing, which seems to be working really well, and it starts to scale pretty well, versus work on new innovations that will make it even better.
Yeah. And maybe related to that, in your view, what is overhyped today and what is underhyped?
What's overhyped, what's underhyped? I think egoistically speaking, I think what's underhyped is physical intelligence. I think just this idea, I think if you like truly internalize it, I think if everybody truly internalized it, they would view the world differently. You know, the fact that you can have a single language model that is trained on everything, be the best at each specialist tasks, be better than specialists at those tasks. I don't think many people truly internalize this because it's not how the world works, right? Like if you have your startup and you want to compete with someone, the way you do this is by focusing on that one thing and doing it really, really, really well, right? Like specializing very, very well. And that's the only way you can compete against a big company because they're spread too thin. But it seems like with these models, that's not the case. It's the more things you tackle, the better the models get at each one of those things. And that's very counterintuitive. And in the physical world, it's just as counterintuitive, right? Like you would think that the best way to get a robot folding laundry in the home is by focusing on robot folding laundry in the home. That's the way to really, conquer that market. But I think the way it's going to pan out is that it's not the best way to actually solve that problem. The best way to solve this problem is to tackle all of robotics all at once. All robots, all tasks in all markets. And these will end up being the best robots at folding laundry in a home. So I think that's undervalued. What's overvalued? I'm not sure. It feels like there's just a lot of hype in the sphere. It feels like there's a humanoid about to knock at your door and like show up at your doorstep and just like do everything for you. I don't know if I should attribute this overhype to humanoids in particular, but I think just like in general, the expectations are through the roof, and I don't think the tech is quite there yet.
In your minds, like what are maybe some of the more unanswered research questions today?
Yeah, and I think the big one is like there's a lot of different data sources, right? Like what makes robotics very different from like how LLMs have tackled it? There's kind of like two parts of it. The first problem is like in pre-training. LLMs got the gift of the internet, right? And we're going to try to use that as much as we can to our advantage. We think it's important, but it's not going to go the same distance that it has gone for language models. And that's the big data question. Like, where do we get this diverse source of data? There's a lot of different people trying different approaches, and some of it looks like do you just strap like AR glasses to people and like collect human what we call egocentric video. That's like one approach. The other approach is like you hold things that are, look like little robot claws, and you like go around doing a bunch of tasks. These don't require robots, so you can get a lot of them out into the world. You can scale it. The third approach is also like to actually take the robot, like get it out there. And the nice part about that is you can think about like a deployment data flywheel where like once the robots start getting good enough to actually do stuff, now they're collecting lots of data, and they're going to collect way more data than's like ever shown up on the internet pretty quickly. Like once they're actually like creating value in the real world and experiencing things in ways that are sort of economically incentivized, sort of amenable to scale. So I think that's like what that data source is going to be, like what that right approach is like one of the big trillion-dollar research questions. Like nailing that down and understanding like how do you need to like ready the technology? How do you need to bootstrap things? How much work do you need to put into bootstrapping? Or like how do you invest your like marginal dollar in like this data source or this other data source? And that also kind of brings me to a second point, like what a really big research question is, which is language models, they're easy to evaluate too, because you can just like spin up some GPUs, you can generate some tokens, and it lives in this world of text. It's been very amenable for things like reinforcement learning, where you have some sort of verifier that also runs in the computer. You take a bunch of tokens, you're like, the verifier, then on the same computer will say like yes or no, does this like pass the test, and that becomes your reward. And you can actually use that to improve the reasoning capabilities of language models. For robotics, that doesn't quite work because you actually have to like do stuff in the real world. So you can't just like, do this thing a million times and take an update. That's going to take forever. So we need to figure out that, and part of that is like, what do evaluations look like? How do we answer all these questions about the value of data, and how do we get this sort of like reinforcement loop working really well? And part of that comes down to how do we evaluate policies? So I think those are like two of the sort of biggest research questions. What's the right data sources? Where do we get the data? And then how do we evaluate the policies that are trained on that data? And how do we potentially use that to push the performance frontier as well?
And also there's unlimited number of research problems. Like you can do research on anything. Even if it works, you can do research on how it works or why it works. So I think the failure of research is less that you failed at solving a problem. It's more that you picked the wrong problem to solve. And there are so many things that people are working on in the industry, but I think it's quite hard to determine which are the ones that actually are going to move the needle.
And maybe switching gears to the company journey a bit, I think one of the most impressive things about Pi is the talent density. The best people have options, and it's rare to see so many people come together. Perhaps OpenAI is maybe the other company that managed to do it. Like, how did you convince so many of the best researchers to come together, work together on the same mission?
I don't think I should get a lot of credit for that. I think it's one of those things, you probably realize it in your startups too, that if you get a few people at the beginning that are really, really good, that set the bar, then it's much easier to attract the next one. And if you don't lower that bar at any point, then it's just this self-fulfilling promise where like it just happens, right? Like people are attracted to working with very good people, and if they see that you have very high talent density, they want to come to you and work with you. So I think it's more about the rigor of keeping that bar and not hiring too quickly and being really careful about that. I would also say that at that point when we were starting the company, there weren't that many options. If you want to do large-scale robot learning, there weren't many companies where you could go. There were a few big tech players, but I think everybody who worked in those companies realized how slow it is and why they would want to do it differently. And I think the same applies to OpenAI. The reason why it was so much easier for OpenAI is that it was a contrarian bet at the time. They had a lot of conviction that this is going to work. And you had the chance to just like join this group of really good people that are just willing to like bet everything on it. So I think we were not as ahead of the time as OpenAI was, but I think we had a similar thing going for us.
And given the scale and ambition of what you're trying to build, what gave you the conviction that this needs to be a separate company, a separate startup, and not part of a company that has 10x the resources that a startup would?
Yeah, I believe that every company has a reason to exist. There's like one fundamental reason why they exist, and that's their top priority. And then what that means in practice is that every time you have a decision to make, you have to weigh these different priorities and estimate the downside and upside, and it slows you down. So for instance, if you have a decision to make, let's say that in order to really solve this problem, you need to deploy robots out in the world. For us, it's a very easy decision to make. This is what's going to push the mission forward. We should do it no matter what. So it became clear to me that if this problem is truly solvable, and at that point I thought it was for the first time in my life, then it deserves an organization whose sole focus is to solve the problem. And that's why we started it.
You're tackling a very, very important problem. Did you feel like the smartest people in your industry are working at robotics startups and are kind of aligned towards the common vision of achieving what you guys want to achieve?
I think it's changing as we speak. I think when we were starting the company, most of the smartest researchers, they didn't think much about robotics. I think they mostly focused on language, vision, those problems. they're more gravitating towards OpenAIs of the world, or Anthropics. I think now when the problem is getting more and more solved, it starts becoming boring, and it starts becoming more of a race of who is going to implement this or that feature faster. So I think that wave is changing now, where people are looking, or the best researchers, I think, are looking for the next big thing, for the next thing that is not solved, but it's on the brink of being solved. And that's where I see many, many more people, even from these companies, thinking about robotics, starting to tackle robotics problems. So yeah, I think it changes over time.
And then from the early days, the Pi has been open sourcing a lot of stuff. How have you guys thought about that, pros and cons of doing that, and why go down that path from the early days?
Yeah, maybe I can talk about the reasons, and you can talk about some of the experiences, what we've seen the community do. We thought that early on, actually not just early on, I think at any point, the biggest risk for us, the biggest reason why we would fail is because the science just doesn't work out. Like the problem is too hard. So I think from that, it follows that if there is anything you can do to increase the probability of the problem being solved, you should do it. Because if it's not solved and you don't reveal anything, it doesn't matter. You just have a fence around the desert. And it was very clear that by open sourcing our models, we will increase the probability of the problem being solved. We'll have more people aligned with our vision. We'll have more people pushing performance of these models. We'll also learn from them how they evaluate them, how they use them. And then the side effect of that is it's also extremely attractive to everybody coming to Pi. You basically have a jumping board to really show the world how good you are, how good the models are that you're doing. And the best researchers want to showcase their work to the world. So we thought that the upside was humongous, and there was no one really doing this at the time. And the downside was very, very minimal.
Mm-hmm. Yeah, and I think what it did, especially for academia, young startups trying to think about like what is actually buildable, is it kind of gives you like something to kind of ground yourself in the state of the art. And I think before we open sourced something, like that wasn't doable. I mean, the labs were working with these very small models. The performance like wasn't nearly as good as what we were getting, and by being able to like put this out there and have people start using it, I mean, not only does it like sort of help with some of this technology risk, there's a lot more people working on this problem. There's kind of like more exploration in different directions, but it also kind of like primes some people to start thinking about like the most important problems, the actual bottlenecks, and for startups and other people, they can start thinking like, what should I start building now that might put me in a good position, and the robotics industry as a whole, so that in a year, a couple of years, there's the industry is actually prepared, not just us. And I think that is like an important thing, and it is something we've seen. I mean, we recently released like a partnership blog post where we worked with a couple companies. We explained how that went, and they started by using our open source model, and that was like the easiest way to kind of get them onboarded, let them sort of put their foot in the water, understand like are things ready, and then we worked with them obviously to improve it, and that was the sort of point of the blog post. But it now gives a lot of people this like starting point, and I think that's just going to help the industry as a whole grow faster, and there's a lot of knock-on effects in terms of like how that benefits us as a company, but also just like the world more broadly.
Yeah, and maybe related to that, I think you have such an untapped market universe to go after. How does Pi think about the types of tasks you want to prioritize, the types of partnerships, the types of deployments? Because data is a bottleneck, and you can go in so many million directions. You can partner with so many different people. Like, what mental models do you have around prioritizing tasks and partnerships?
Mm-hmm. Yeah, I mean, we're still a research-first company, right? And I think what that means for tasks is we want to pick tasks that give us kind of like the maximum rate of learning, like the highest gradient. So these are usually tasks that are kind of like at the edge of our capabilities, but still like meaningfully grounded. We have generally tried to avoid sort of playground tasks that aren't like real, just to kind of keep ourselves focused on like what are actually the challenges that arise when you try to put robots out into the world, because like that in and of itself is useful. But we also don't like try to take moonshots to tasks that are like so difficult, where you're just going to be sitting at success rates of 0 for very long periods of time. If you've worked on these sort of things, there's like a nice medium where you can kind of like do research, and you can see the success rates go from like 10% to like 80, 90%, and that helps give you signal of like is your method, is your change working, and then do you think it's going to scale? Like, is this something that like we should scale up in the grand scheme of machine learning? And I guess like a lot of that looks, you've seen some of it live, right? With laundry folding was like a really good initial example. I guess as we look more at like deployments, like getting robots out into the world, we looked at tasks like box building, and this was something that was very dexterous, so it was interesting. But it was also like useful, and the way it was typically done is you sit at like an individual like static station and just fold these boxes. So you don't have to worry about things like mobility and safety, and those are really nice if you want to just kind of like move as fast as possible and like focus on the core research questions. So I think that's like kind of like the main filter for those two, and then partnerships. It's kind of similar. People who want to move fast, low friction, just understand kind of the experimental nature of this, but are also still very committed about seeing where it can go, trying it out, running experiments on your own. I think those are all kind of important, and picking the task that is like kind of reasonable given current capabilities is like also important as well.
Yeah, the low friction point is a big one. Like traditionally, how you would go about this is you would find the market with the biggest TAM, where people is really ripe for automation, and you would go all in. Let's say it's manufacturing or something like this, and you would go all in and try to really master that task, because economically it's kind of like the best move you can make. It just moves very, very slowly. You need to understand that task. You need to get on someone's schedule. You need to get all of the parts in. You need to understand what it means for this test to be successful. What are the strategies to actually make that task? And you just move much, much slower. So by being more low friction, we pick something like laundry folding, which you would be surprised, but it's actually fairly close to something like a manufacturing task. It's long horizon, very dexterous, has many similar properties, but it's so low friction, right? Like everybody can understand if the shirt is folded correctly or not, right? You don't need any training. We don't need to get on anyone's schedule. We can bring people's laundry into the office and have diversity of data. It's all very resettable. So like you can, as soon as you fold it, you can unfold it in a fraction of a second. So there are some tasks like this that just allow you to move fast and iterate on the algorithms.
I do want to open it up to the audience for some questions as well. Any questions from folks?
Hey, good to see that there's some, like especially physical intelligence being worked on. One of my questions is that, especially for AIs or robotics specifically, if you look at humans, you compare the memory side of humans is so humans have experience, right? That's how you build all the things. Whereas if you take a model and build a model, can you build experience like a human memory layer or so? Because humans have multi-layers of memory. You have short-term sensory and long-term memory. Do you think about that while building physical intelligence?
It's a great question. We actually have a release coming up talking about this. One thing you'll be surprised by is that all the demos you've seen of all the robots, I'm pretty sure all of them, have no memory. So I think it means even more than you think it does. It means that at every single step, when you're folding laundry, it's as if you just woke up and you didn't even remember what you did a millisecond ago. Right? You just see the shirt right in front of you, and you just think about the next movement, and that's it. And then you fall asleep again, you wake up again. So it's quite counterintuitive that it even works. Right? Like, it seems like even by folding laundry, you should be able to like kind of remember what you did before, and it's like, did you just put that sleeve in, or did you just undo this? Like you should remember this. It turns out that the models find some way around it, but they have no memory whatsoever. This is one of the big problems, one of the big research problems, on how do you introduce memory. Because if you do it naively, it actually reduces performance. It makes it much worse. And the reason is a little nuanced. It's often referred to as causal confusion. And maybe I can explain with an example. Let's say you're a self-driving car, and that's actually an example that I think people usually give for this problem. If you're a self-driving car and you have a lot of data where you press on a on a brake pedal, and then the brake light turns on. It's actually unclear to the model whether the brake light turns on because you press on the pedal, or whether you press on the pedal because the brake light turned on. Because a lot of data just has you pressing on the brake pedal and the light being on. And the more data you collect, the more of a history you have, the more of this bias you have that actually you should step on the brake every time there is a brake light on, which is obviously wrong. And we actually see this a lot. So we've been working on this for quite a while, and we have a release coming up that describes how you can resolve this issue with short-term and long-term memory. But yeah, it's a big open problem.
Cool. A little curious, how should we be thinking about how to even begin to think about these generalist models and how to evaluate them, like the ideal case for evaluation, especially if we want to get to a place where we are able to push new updates almost on like a weekly basis, right? What is like a scalable way, and what is like the frameworks you guys are thinking about? A little curious to think about where your head is at, and what would you imagine an idealized solution to look like?
Do you want to answer it?
Yeah, I mean, as I said earlier, evaluations is a very, very hard problem. I don't think we necessarily have the answer for it. But there are a couple approaches. I guess like one approach is you have a large internal fleet of robots. You just like run in the physical world. You're bottlenecked by the clock speed of the speed of light, whatever the real world runs at, right? Then there's you could also try to use deployments for this, right? So if you have a lot of robots that are out like in the world, maybe you have some sort of like incremental rollout process, but like once you get some sort of level of confidence, you like send out some sort of like A/B testing for customers, and you ride that gradient. But maybe that feedback loop is slower, and it's not something we necessarily have yet because the problem isn't like I'd say fully bootstrapped. The robots aren't actually out there in large volumes doing things that are interesting. And then, I do think SIM is like, a potential candidate, and I guess that's probably why you asked the question. But the main challenges there are, how do you get the right levels of diversity in SIM? How do you get it to, mirror the real world and actually strongly correlate? Do you do this with classical simulation? Do you do this with world models? Still, very much an open question, but I think the SIM probably looks a little bit more like the ideal case where you just like click a button and suddenly you get a score back and it tells you, yeah, this is how well it's going to do. Maybe there's other ways to do it with like offline metrics, and this is things that aren't necessarily running the robots in SIM, but values that you can find in the training process that correlate very well with like what is actually going to be the real world performance, because that will always be your North Star. You're never going to fully get rid of that, but you can try to find ways that things sort of correlates that help before you actually like spend a ton of time and resources evaluating these things in the real world, and potentially that comes from SIM, potentially it comes from like other sort of offline metrics that you can concoct.
I'm really glad you asked this question, because that's speaking to this like work on the right problem. I think this is absolutely the right problem, and it's also a problem that is going to get worse. The better the model gets, the worse the problem gets. Because the models get more capable, so you need more samples to distinguish between 99.9 versus 99% success rate that you needed between 20 and 40%. But also they are more broadly applicable. So now you need to evaluate it across many, many tasks, many more robots, and so on, and it keeps on getting harder. So yeah, you're working on the right problem.
Appreciate it. Maybe just asking the question a little bit differently. The goal for physical intelligence is being something truly generalizable. What do you imagine that Turing test to look like for like true generalizability? Like, how would you know when you have reached it? Like, how do you know when physical intelligence achieves its goal?
Yeah. I think I remember having these debates about language as well. Like there's this Turing test, but like how would you really know?
I think we passed it.
Yeah, it feels like we passed it and nobody cared. Yeah. And I think it's maybe it's going to be similar here, that like we can debate, when would you know, but you'll know. That will be pretty clear, I think. I also think that it might be that the value function, the like value delivered from generalization versus performance would be quite different. I think we spend a lot of time on generalization, how well can your robot, or how well can it respond to a new command that it's never heard before. But if it performs at like 10% success rate with that new command, that kind of like doesn't matter. Like it generalizes a little bit more, but like who cares? So I think it might be that for language it was everything, right? Because when you talk to a chatbot, you're right there. So if it makes a small mistake, you can compensate for that. You can accommodate for that. And the physical world is not like this. If you make a small mistake, you're a millimeter off when you're, I don't know, making coffee, it's a disaster, right? Like everything spills and it's just like it doesn't work. So I think that the difference between how much value you get out of good performance versus generalization might be different for robots than it was for language.
Cool. Two last questions from me. In 10 years, there are clearly going to be big societal changes and implications for the physical labor economy. What is some of the stuff that you're most excited about if you think about that utopian world? And perhaps what is some of the stuff that scares you about it?
Yeah, I mean, I guess in terms of stuff that like excites me, which I guess is probably the easier half of that question. I think there's right now manufacturing is it's expensive. The way you make something cheap is by making it at scale. That's like since the beginning of the Industrial Revolution, that's kind of been the pace of things, the sort of theme. I think with physical intelligence, that can start to change. So with very flexible autonomy, you'll be able to make products that are lower volume, more tailored, more niche. And I think that can bring around a lot of positivity. That's also going to unlock a lot more entrepreneurship. And I just generally very excited to see like what the sort of knock-on effects across the sort of economy are going to be like so much building, so much manufacturing, so much like physical production is currently constrained by the need to scale, the need to invest a lot in expensive factory automation equipment. But I think like as these as physical intelligence gets better, then I think that will start to shift. And yeah, to me that's like probably the most exciting future that I look forward to.
Yeah, I think we are constrained by labor a lot. I don't think we fully realize how constrained we are. And there was this period where electricity felt like this thing that like requires so much to like get it to actually appear. Right? It was right at the beginning where like we kind of figure out how electricity will work, but it was not accessible. It just required so much effort to make it happen. And now you just like flip a switch and it's like right there for you. And I'm really excited about the future where the same thing happens with labor. Right now, the only unit of labor we know is a human, is a person. But imagine when that's not the case and labor is just freely available to anyone. Like it's just like a flip of a switch. I think that's going to be a very, very different world. And it's kind of hard to imagine all the consequences. In terms of things I'm really excited about, we are really sprinting towards the future of aging population. And I don't think there's any other solution in terms of taking care of elderly, but also in terms of making the economy work. I think that's going to be the only way. I'm really excited about what we'll be able to build, like what Michael was saying. In terms of what scares me, I think similar worries to the digital AI revolution. Maybe the advantage we'll have is we'll get to see how that goes and what mistakes were made. But I think the same things apply, whether it's accumulation of power, the change being too rapid, like how we're going to deal with this as a society. I don't think many people realize how fast this is coming.
And final question for you, Karol. You've had a very successful career. You've taken a very long view on robotics in this space. A lot of people in your position might be on a beach, might be relaxing, but you're here working very hard towards a very hard problem. What keeps you going?
I don't think I had that successful of a career and I could just relax on the beach. I never thought about this. Maybe I should have.
With your personal robot, of course.
Yeah. I mean, I always wanted to work on this. I've been fascinated by this. But yeah, I always wanted to make robots happen. And for a long time, it felt like no one really cared. Like the robots were extremely disappointing. These like really boring machines that just like go from A to B and that's it. And that seemed like such a downer. Like we had this future like painted for us and nobody's working towards it. So I was just happy to even be given a chance to work on the problem, even if at that time the problem just felt absolutely unsolvable. But it's just fun to work on something that like you think can be meaningful and is interesting. So I was already happy then, and now being able to actually see a solution, or at least see the light at the end of the tunnel, that's just really, really exciting. Like if you worked on something your entire life and you thought that it would never be solved, and then all of a sudden there's an opening, and it's going to be really hard, and there's a lot of risks, and it might not work, but there's an opening, there's the light. And once you see that light, you can't unsee it. So I don't think a beach is an option.
Thank you so much for working on this mission, and thank you for coming. I think this was one of the most profound talks we've had here, so really appreciate it. Thank you.
Thank you.
Thank you.